Hello students, in this lecture we will talk about linear programming problem. Okay, so before discussing about linear programming problem, let me tell you about optimization problem. Okay, because linear programming problem is a type of optimization problem. Optimization problem contains two things. The first one is the objective. Okay, so this is the objective, that is to be maximize or minimize. Okay, and the second part of optimization problem is constraints. Okay, so constraint could be one constraint or it could be n number of constraint. Okay, so this is the limitations. Okay, so in optimization problem, one objective is given to us, that is to be maximize or minimize along with n number of constraints. Okay, so in our objective optimization problem, our main objective is to optimize the value of the objective, okay, under the given constraints, under the given limitations. Okay, so one type of the problem that we're gonna discuss throughout this course is linear programming problem. So again, linear programming problem also is going to have objective, okay, and objective will look like this: maximize or minimize z equals to c1 x1 plus c2 x2 plus dot dot plus cn xn. Okay, so this is the objective subject to the constraints. So constraints are going to look like this: a11 x1 plus a12 x2 plus a1 n xn less than equals to or greater than equals to or equals to v1. So this is the first constraint. Similar to this constraints, B may have a small m number of constraints. So last constraint will look like this: a m1 x1 plus a m2 x2 plus dot dot a mn xn less than equals to, greater than equals to or equals to vn. Okay, so here we have a small m number of constraints. So along with these m number of constraints, we're gonna have some non-negativity constraints. So non-negativity constraints are x1 comma x2 comma xn greater than or equals to 0. Okay, so this is the general form of linear programming problem. Okay, why this is linear? Because objective and the constraints, all the constraints are going to be linear. So that's why this is called linear programming problem. So if either one is not linear, objective or the constraint, then this problem will become non-linear programming problem. Okay, so I hope this definition is clear to you. Okay, so in linear programming problem, the objective and all the constraints are going to be linear. If either one is not linear, then this problem will become non-linear programming problem. So let us write down the compact form of the linear programming problem. So compact form. Okay, this entire linear programming problem can be written as maximize or minimize z equals to, this can be written in form of summation I equals to 1 to n c I x I. Okay, c here is known as the cost of an object and c is known as the decision variables. Subject to the constraint summation j equals to 1 to n a I j x j less than equals to or greater than equals to or equals to bi for every I equals to 1 comma 2 comma n. So this entire expression actually representing total n number of constraints. Okay, why n number of constraints? Because if you pick I equals to 1, so this is going to be a11 x1 plus a12 x2 plus dot dot a1 n xn less than equals to or greater than equals to or equals to v1. Similarly, if you pick 2 I equals to 2, then it is going to be a21 plus a21 x1 plus a22 x2 plus dot 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 a2n xn less than equals to greater than equals to or equals to bi. Okay, so this is the compact form of the linear programming problem. Okay, now let us discuss about the matrix form of the linear programming problem. Okay, so in matrix form of the linear programming problem, it could be written as, okay, so this is matrix form of the linear programming problem. So in matrix form, this can be written as maximize or minimize z equals to cx subject to the constraint a x less than equals to greater than equals to or equals to b. Okay, and along with this we have to write down the non-negativity constraints. So non-negativity constraints are x greater than 0, where okay, so where the c is now this C is going to be a matrix, this is also a matrix, this capital A is also a matrix, this capital small x is also a matrix. So, where C is equals to, okay, so this can be written as C1 C2 dot 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 Cn, okay, small x is equals to x1 x2 dot dot xn, okay. So, if you multiply C and x, then you will get this equation, okay, summation Ci xi, okay. So, the dimension of this matrix is 1 by n, and the dimension of this matrix is n by 1. So, if you multiply C and x, you will get one matrix or dimension 1 by 1. That means you are going to get this scalar value. Okay. Now, okay, sorry about it. Now, capital A is going to be equals to a matrix of size m by n, okay. So, the first row is going to be A11, A12 dot dot A1n, okay, and the second row A21, A22 dot dot A2n, and the last row is going to be equals to AM1, AM2, AMN, okay, and the dimension of this is equals to myn, where m is the total number of constraints and n is the total number of decision variables, okay. So, decision variable is represented through this x, okay. Now, b is equals to b1, b2 dot dot b m. So, the dimension of this is m by 1, okay, m number of rows and 1 number of column. So, that is how we can represent a linear programming problem in form of matrix, okay. So, next we are going to discuss about canonical form, okay. So, canonical form, sorry. Okay, so in canonical form, your objective always is going to be maximize, okay. So, there will be only maximization problem in canonical form, there will not be any minimization. If any minimization problem is given to us, then we can convert that minimization problem into the maximization problem. So, maximize z equals to summation I equals to 1 to n Ci xi subject to the constraint summation j equals to 1 to n aij xj less than equals to bi for every I equals to 1 comma 2 comma 3 up to n. Okay, so here in canonical form, uh, if maximization problem is given to us, then easily that is already in canonical form. If any minimization problem is given to us, then we can convert that into the maximization problem. And second thing is this constraint. Okay, so in canonical form, all constraints are going to be the greater than less than equality constraint. Okay, so if any minimization problem is given to us, let us say minimize z equals to summation, okay, I equals to 1 to n ci xi. Okay, so we can convert this minimization problem into the maximization problem by multiplying it by -1. So maximize, okay, this can be converted into the maximization problem. So instead of z, we're going to write down z star. So this is equals to minus I equals to 1 to n ci xi. Okay, so if any minimization problem is given to us, then easily we can convert that into the maximization problem. Second thing that is required to convert one form of LPP into the canonical form is this constraint. Okay, so all the constraint in the canonical form are going to be less than equality constraint. Okay, so for example, if any constraint in the given LPP, okay, let us write down one constraint. Okay, this is a 11 x1 plus a12 x2 plus dot dot a1 and x1 xn is greater than equals to v1. Okay, so easily we can convert this greater than equality constraint into the less than equality constraint by multiplying with -1 both side of this constraint. Okay, so this constraint will become minus a11 x1 minus a12 x2 minus a1n xn less than equals to minus b. Okay, so this is the process of converting greater than equality constraint into the less than equality constraint, and here this is the process of converting a minimization problem into the maximization problem. Okay, so let us move to the next form of the LPP, which is the standard form. Okay, so next is standard form. Okay, so the standard form of LPP is look like this. Again, maximize or minimize z equals to c1 x1 plus c2 x2 plus cn xn subject to the constraints a11 x1 plus a12 x2 plus a1 n xn is equals to b1 a11, not 11, actually this will be 21 x1 plus a22 x2 plus a2n xn equals to b2, and similarly we can write down the last constraint, which is going to be a m1 x1 plus a m2 x2 plus dot dot plus a mn xn is equals to b. So this is the standard form of LPP. So here there will not be any greater than equality constraint or less than equality constraint. All the constraint will have the equal sign. Okay. So if in the given LPP any constraint is greater than equality or less than equality constraint, then easily we can convert that into the equality constraint. So in the next lecture we'll see how can we convert a given LPP into the standard form.